Welcome. If we want to investigate the geodesic flow and sectional curvature and its properties, we need a lot of examples. And one way to get examples is by looking at level surfaces, so codimension K manifolds in a given manifold. And I'm using this theorem, which I think is very nice. If you have a manifold of dimension n, we can just take an arbitrary map from the vertices to the finite set from 0 to k, and then we get a n minus k manifold, or empty. It can also be empty. So here we see an example. So the function takes here values, two values, values 0, 1 on the vertices of a two manifold, and you get always a one manifold, which is a collection of one-dimensional curves. So what we want to do is directly compute the geodesic flow within that surface and not have to do the barycentric refinement. The reason is that this set is a priori only an open set. Like here, for example, these are all triangles and edges where the function changes value. So this edge is contained because the value is different. So there are different colors, right? And so we have two different colors, and we take just all the simplices where the function changes color, and that gives us then a one-dimensional curve. But this is actually, you see these triangles here are together here in the ambient manifold, but they are actually not connected because the color is the same here. So it really works very nicely. But in order to do the geodesic flow, what we could do is we could look at the barycentric refinement, meaning we are producing the graph first, where the triangles and edges are the vertices of that graph, and then we connect to if one is contained in the other. So that's the definition of that graph, and then we take the Whitney complex, which gives us then again a one manifold, and this one manifold is that curve, represents that curve then. And so of course if we have then that curve, we can just look at the geodesic flow as we have defined it. Maybe a reminder about the geodesic flow. It's a very, very simple idea. What we do is we take the maximal simplices and we put an order on each of these maximal simplices. This produces a frame bundle. I call this P, like, you know, in classical mathematics, if you have a principal fiber bundle over a manifold, you call this usually P. And then we have here just a permutation on that. And the permutation is very simple. So we have a simplex 1, 2, 3, 4 here. So what we get is we get then 2, 3, 4, and 5 is then just the opposite, right? Every vertex in a maximal simplex has a dual one. So this duality is very, very general, right? When you have a K simplex, there is associated to it the n minus k minus one dimensional sphere, which is the intersections of unit spheres. That's the definition of manifold, that these are spheres. And then we can take them as boundaries of balls, kind of a CW complex, an abstract finite CW complex, which is then the dual manifold, which is again a manifold of the same dimension, but it's not very simplicity complex. Everything is finite again, and very important are the bones, which are the q minus 2 dimensional simplices. Maybe I just explain that here. So that's kind of the cool toy. I love that toy, and because we can play with simplices in 3 dimensions, which is not that intuitive. So what you have here in a 3 manifold, the bones are just edges. And in this case, this would be the bone is that edge here. So, and there are 4 tetrahedra, right? Four simplices are attached to it. And you can do that. So in this case, maybe here I have another example where we have 1, 2, 3, 4, 5, 6, 7, 8 points. So this bone here has 8 simplices attached to it. So it's kind of not so well visible here, but you can play with this tetrahedra. So the bones are the q minus 2 dimensional simplices, and they define a one-dimensional sphere, kind of a circle. Right? That's what happens when you take that. So what happens here, this is a cyclic structure, right? It has all these simplices which are hinging on it. It's an open set, by the way. Again, this is an open set. All the simplices which contain a given edge form an open set by definition. This is of the Alexandrov topology. So it's a non-Hausdorff topology which has as atoms the stars, which are just the simplices which contain a given simplex. So if you have an edge, all the simplices which contain that edge, that open set, which is called the star, looks a little bit like a star, and this star is actually for a codimension 2 simplex, it's just a circular object in a manifold. And so that can be used now for defining sectional curvature, because what we can do is we can just look at the geodesic sheet. So we take a bone, this defines then a two-dimensional structure, which we can then use to compute the curvature of it. And we have talked about this last time. The best curvature I have seen, and it really works very, very well, is the form curvature, the two-form curvature. I defined K-form curvatures in general, but and this has been defined by Ishida and Higuchi just in the 90s. In the case of two-dimensional planar graphs. But it works in general in arbitrary dimensions. You can do that, but we need it just in 2 dimensions. And here I just give you the case. I have an example of a small projective plane here, which has 31 vertices, 90 edges, and 60 triangles. Other characteristic, of course, is 1, like for all projective planes. And then we have these are actually substructures of the dual graph, or the dual simplicial complex, which is no more a simplicial complex, it's a CW complex, and these are the cells. So each of these circular structures is actually corresponds to a bone, corresponds to a vertex here in this case, because we are in 2 dimensions. And then in this case, the curvatures are actually all positive. 1/18, 1/30. For every bone, we have a curvature. Defined this last time. 1/18, 1/30, 1/45. And adding up all these curvatures is Gauss-Bonnet. That's very, very important that we have Gauss-Bonnet. In general, all these curvatures which are defined last year, K curvature, they are all satisfy Gauss-Bonnet. So also this now satisfies Gauss-Bonnet, but just for that 2-dimensional structure. So this could be kind of a part of a higher dimensional manifold. You can do that in arbitrary manifolds. We get notions of sectional curvature. So that was kind of one of the reasons to have a geodesic flow is we want to have from the bone to extend the bone and build a larger structure and build this geodesic sheet. I talked about this 2 weeks ago. We want to generate thousands and thousands and millions of manifolds, and that's the way how you can get from a given manifold. For example, you start with a 5-dimensional manifold, which has been given in a library, and you produce random codimension 2 manifolds, and you get random 3 manifolds. Or codimension 1 manifolds, you get random 4 manifolds. So what you can then do is you don't want to compute the geodesic flow in the ambient space or just by doing barycentric refinement. These are open sets, right? A priori, these are open sets, how I define this manifold. Like here, right? This is an open set, but this defines naturally a 1-dimensional manifold. We want to directly compute the geodesic flow within this manifold. And here comes the Schild's ladder idea. Of course, it's completely different than what we have, but I've used this Schild's ladder idea since the 90s. I consulted that book, which is my weightlifting book here, and it has the Schild's ladder in. It's from the 70s, so in the 70s, this was actually cutting edge. When this, just shortly after Schild was defined, this numerical method, they already included that in that book, which is also from the 1970, 71, 72, depending on the edition. And it's a very simple idea, and I used this in the 90s to make illustrations for that book of Moser script And so there's actually just, I made lots and lots of pictures, but this is just the only picture which kind of really came in from that thing. It's written in Povere in the ray tracer. So all the numerical computation is done within Povere, which is a programming language which is pretty powerful. But of course it has to be simple enough. And this idea of Schild is very, very simple. What you do is, if you have a manifold and you want to compute the geodesic flow, what you do is you just take, you have it embedded in an ambient space. By the way, that's always possible for every Riemannian manifold by Nash's embedding theorem. So, in principle, you can do that for every manifold. And then what you do is you look at the tangent space in the ambient space, which sticks out, right? And then you can take that, make the, a little step, and then puff, you glue it back to the manifold. So it's somehow like you are evolving in the ambient space, but you are glued to the you are glued to the surface. It's a very nice numerical method, and it works very well. I made some movies also last semester. You can with Povere, and you can compute the geodesic flow pretty effectively without solving the differential equations, which are, a little bit. I mean, you have to implement the Christoffel symbols, have the Riemann metric first, and differential equations are messy. Now, what happens here? We want to do something similar. We want to actually have a geodesic flow on these simplices, which are part of that manifold. But of course, we cannot just use this map here, because we get out of the manifold in general. So that's what happens here, right? We get out of the manifold if we just evolve with the usual geodesic flow. In this case, it works like 1, 2, 3. So the first one which we have is kind of has a dual, that has a nice dual, right? It's the kind of reflection at this wall, gets us here to 4. Now we kind of continue. We cannot continue here, right? When we do that, the 2, 3, 4 prime and 2, 3, 4 would give you 3, 4, and then 2 prime, 3, 4. 2 prime is outside the manifold. So what we do is, if we are outside the manifold, what we do is we are just not take the first point, we take the second point, and we do the same construct. So we just go with the second point if we have not the first point. So that's much more efficient, much faster than doing the barycentric refinement and then do everything in that much larger manifold. That's it for today.